How would you maximize your calendar by removing the fewest overlapping meetings? Non-overlapping intervals is a Pattern Mastery 100 favorite and a go-to at Google, Meta, and Amazon to test your greedy reasoning with intervals. Over 30% of candidates make the wrong removal choice or miss the best sorting strategy. Nail this and you'll master scheduling and optimization problems in interviews. Let's break down non-overlapping intervals using the basic approach, a proven strategy for greedy interval problems. Given a set of intervals, start, end, find the minimum number of intervals to remove to make the rest of the intervals non-overlapping. List of intervals, unsorted, may overlap. Integer, minimum number of intervals to remove. Think of cleaning up an overloaded meeting calendar. What's the smallest number of meetings you need to cancel so that no two overlap? Interviewers might ask, how do you optimize a schedule to fit as many appointments as possible without conflicts? What's tricky? Choosing which intervals to remove for minimal impact. A greedy approach, sorting by end time, works best. If you always pick the interval that ends earliest, you leave more space for future intervals. Classic greedy logic. Sort intervals by end time, not start. Initialize end to -infinity and count to 0. Loop through the intervals. If the current interval start is greater than equals previous end, keep it and update end. If not, remove it, increment count, since it overlaps with the last chosen interval. Let's clarify. You're maximizing the number of non-overlapping intervals, so removal count equals total, max non-overlapping. Sorting by end time ensures each choice leaves the most room for what comes next. Edge cases. No intervals or only one, return 0. All intervals overlap, remove all but one. Sort intervals by end time. Initialize end equals inf, count equals 0. For each interval. If interval.start greater than equals end, keep it, update end equals interval.end. Else, overlap, increment count, remove this interval. Return count. Let's try to implement it using solution 1. We begin by defining a class called solution. This class will contain our method for determining how many intervals we must remove so the rest no longer overlap. Here we define our method erase overlap intervals. It takes a 2D array of intervals, each one represented as start, end, and returns the minimum number of intervals we need to remove to eliminate all overlaps. We store the total number of intervals in n. This helps us manage loops and compute the final result. This is a simple edge case. If there are no intervals, then obviously we don't need to remove anything, so we immediately return 0. Next, we sort the intervals by their starting point. Sorting them helps us process intervals in a clean left-to-right order, like lining up events on a timeline from earliest start to latest start. This sorting operation takes O(n) log n time. Here we create a dynamic programming array called dp. dpi will store the length of the longest chain of non-overlapping intervals that ends at interval I. We fill the dp array with ones. This means each interval by itself can always form a chain of length 1, even if it doesn't connect to any others. We create a variable max chain to keep track of the longest chain of non-overlapping intervals we find. It starts at 1, since every single interval alone counts as a valid chain. This begins our outer loop. For each interval I, we'll try to extend chains built from previous intervals. Now we begin an inner loop running over every earlier interval j. We're checking whether interval j can come immediately before interval I without causing an overlap. Because of the nested loops, this dp approach runs in O(n)² time. This line checks two conditions. Intervals j1, less than equals intervals I0. Interval j ends before interval I begins, meaning they do not overlap. dpj, plus 1 greater than dpi. If adding interval I after interval j forms a longer chain than what we've recorded so far, then we should update our chain length. In plain language, can interval j lead into interval I, and if so, does it give us a better chain? If the conditions hold, we update dpi to show that the best chain ending at I is now 1 longer than the best chain ending at j. After processing all earlier intervals for I, we check whether the chain ending at I is the longest one so far. If it is, we update max chain. Finally, we compute how many intervals must be removed. N is the total number of intervals. Max chain is the largest number of intervals we can keep without overlap. So the rest, n, max chain, must be removed. And that's how this algorithm works. It first sorts the intervals and initializes a dp table, then checks all earlier intervals to build the longest possible chain of non-overlapping intervals. Solution 1. Test case 1. Let's test our function using this input, 1, 2, 2, 3, 3, 4, 1, 3. Each pair represents an interval with a start and end time. Our job is to remove as few intervals as possible so that the remaining ones do not overlap. When we sort these intervals by start time and apply our dynamic programming chain building logic, we discover 1, 2 fits without overlapping. 2, 3 fits after that. 3, 4 fits after that. These three form a clean, non-overlapping chain of length 3. The interval 1, 3, however, overlaps with both 1, 2 and 2, 3, meaning it cannot fit into the chain without causing conflicts. Since we have 4 intervals total and the maximum non-overlapping chain size is 3, the number of intervals we must remove is 4 to 3 equals 1. And that's exactly what our program outputs, 1. And the expected result also matches perfectly, 1, confirming that our DP-based interval selection logic behaves exactly as intended. So, our implementation is correct. The algorithm successfully finds the largest chain of non-overlapping intervals and computes the minimal removals, efficient and accurate. Now let's try another implement approach using solution 2. We start by defining the solution class. This is just the container for our optimal, greedy approach to removing overlapping intervals. This method, erase overlap intervals, takes a list of intervals, where each interval is start, end, and returns the minimum number of intervals we need to remove so that the rest don't overlap. First, we handle a simple edge case. If there are no intervals, then there's nothing to remove, so we return 0 immediately. Here's the key greedy insight. We sort the intervals by their end time. Why end time? If we always keep the interval that finishes earliest, we leave as much room as possible for future intervals, just like scheduling as many non-overlapping meetings as you can in a day. This sorting step takes O(n) log n time, where n is the number of intervals. We create a variable removals to count how many intervals we decide to remove because they overlap with the ones we keep. We track the end time of the last interval we decided to keep using prev_end. We started at integer.min_value so that the first interval we encounter will always be considered non-overlapping and can be chosen safely. This starts a loop over each interval in the sorted list. Since we already sorted, we're going from the earliest finishing interval to the latest. This loop runs in O(n) time. Here we unpack the current interval into 2 variables. Start, when the interval begins. End, when the interval ends. This just makes the code easier to read. This if checks whether the current interval does not overlap with the last one we kept. If start greater than equals prev_end, it starts at or after the previous interval ended, so there's no overlap. In that case, we're happy to keep this interval. When there's no overlap, we update prev_end to this interval's end time. That means this interval is now the last kept interval we compare future ones against. In the case of overlap, we increment removals. Because we sorted by end time, we're always keeping the interval with the earlier end and effectively removing this overlapping one. We don't change prev_end here, we keep the previous interval and discard the current one. We return the final count of removed intervals. That's exactly what the problem is asking for. And that's how this algorithm works. It first sorts the intervals by their end time to set up a greedy choice, then walks through them once, keeping only non-overlapping intervals and counting the rest as removals. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input. 1, 2, 1, 2, 1, 2. These intervals represent 3 events that all start at 1 and end at 2, meaning every interval completely overlaps with the others. Here's why the solution works. The algorithm sorts the intervals by their end time, but in this case, all 3 have the same end time, so the order stays the same. We then walk through the intervals greedily. The first interval, 1, 2, is always kept, since start greater than equals prev_end. We set prev_end equals 2. The next interval, 1, 2, starts at 1, which is less than 2, so it overlaps. We increment removals to 1. The third interval, 1, 2, again starts at 1, still less than 2 overlap again. Removals becomes 2. Since only one interval can remain without overlapping, we must remove the other 2. And that's exactly what our program outputs, 2. And the expected result is also 2, confirming the algorithm handled this fully overlapping case correctly. So, our implementation is correct. The algorithm successfully identifies how many intervals must be removed to eliminate overlaps using a clean greedy strategy, efficient, accurate, and reliable. Quick recap time. We tackled the classic calendar cleanup problem. Remove the fewest intervals so the rest don't overlap. Breakdown recap. Conceptually, we're optimizing a schedule. From a pile of possibly overlapping intervals, we want the smallest number of deletions so what remains is conflict-free. Assess recap. We compared options and landed on a greedy strategy. Brute force is impractical here, but if we always keep the interval that ends earliest, we leave maximum room for everything after it. This directly maximizes the number of non-overlapping intervals and, by complement, minimizes removals. Structure recap. The plan was straightforward: sort by end time, sweep once, and keep an interval only if it starts at or after the end of the last kept one. Every time we see an overlap, we count a removal. The final count is the minimum deletions required. Implement recap. We implemented this flow on LeetCode and the solution executed cleanly without any errors. Check recap. We verified the logic with LeetCode's runs, confirming that it behaves exactly as expected and passes the test cases, including edge scenarios. Key takeaway: when scheduling is involved, earliest finish first is a powerful greedy pattern. By maximizing what you can keep, you automatically minimize what you need to remove.